Welcome to The Explainer. All right, today we're going to dig into a concept that is right at the heart of science, a phrase you have definitely seen a million times: statistical significance. So let's just kick things off with a huge question. When you see a headline that says, some new study proves something, or a new drug works, what does it actually mean for that result to be significant? Well, for decades, the answer has felt super simple. A result gets this significant stamp of approval if its p-value is less than 0.05. This little number has been the gatekeeper, the bouncer at the club of scientific discovery. But here's the kicker. What if I told you that this so-called objective rule isn't objective at all? That it's actually the messy, controversial result of a bitter feud between two rival camps whose ideas were never ever meant to be mixed? Okay, so to really get this, we have to go back and meet the guys behind the feud. Let's meet the rivals. So in one corner, you've got the legendary R.A. Fisher. He saw statistics as a flexible tool, kind of like a detective sifting through clues after an experiment to see how strong the evidence is. And in the other corner, you had Jerzy Neyman and Egon Pearson. They saw statistics as a rigid machine for making decisions, something you set up beforehand to minimize mistakes over and over again. These are two totally different ways of looking at the world. Fisher's whole approach started with what he called the null hypothesis. It's a simple idea, really. You just assume there's nothing going on, that your new drug does nothing, that there's no effect, and the whole game was to see if your data was surprising enough to, well, nullify that boring assumption. And this brings us to his big invention, the p-value. So what is it? A p-value just asks one question. If there's really no effect out there, how weird is the data I just collected? A tiny p-value, like that little shaded area you see, means your data is really surprising. And that surprise is your evidence. It's strong evidence that your no effect idea is probably bunk. It's a sliding scale of evidence, not a simple yes or no. And believe me, Fisher's ideas are everywhere today. It's not some obscure historical thing. I mean, if you've ever run into something called an ANOVA test, that F in the F ratio, yeah, it literally stands for Fisher. His stuff is foundational. Okay, so let's switch gears and talk about the other guys, Neyman and Pearson. They weren't thinking about a single beautiful experiment. They were thinking about problems like quality control on an assembly line, where you have to make thousands of decisions and you just need a system to make sure you're not messing up too often in the long run. And their whole approach was just fundamentally different. You had to set all your rules up front before you even saw a single data point. You'd say, okay, here's my main hypothesis, and here's my alternative. Then you draw a line in the sand. They called it alpha, and that was your fixed, unchangeable rule. And you can really see their philosophy right here. There's no interpretation, no shades of gray. You predefine a rejection zone. If your data lands in that zone, boom, you reject the null. If it doesn't, you don't. It's totally mechanical, like flipping a switch. There's no talk about the strength of the evidence. Okay, so you see the problem here, right? We have two totally different systems with two totally different goals. Fisher's flexible evidence gathering and Neyman Pearson's rigid decision making. They are fundamentally at odds. And yet, the method that most scientists use today just mashes them all together into, well, very unhappy marriage. Yep, this Frankenstein's monster of statistics is called Null Hypothesis Significance Testing, or NHST for short. And it's this really awkward hybrid that grabs some ideas from Fisher and some from Neyman Pearson, creating something that, honestly, both sides would have absolutely despised. This table just lays it all out, clear as day. Look at this. NHST takes Fisher's p-value, remember his flexible scale of evidence, and it treats it like Neyman Pearson's rigid line-in-the-sand decision rule. It uses the p-value to make a hard yes-no decision, which is something neither side ever intended. It's kind of the worst of both worlds. So you might be thinking, okay, neat history lesson, but who cares? Well, this philosophical mess has huge real-world consequences. And the best way to see that is by looking at the two big ways you can be wrong when you're testing a hypothesis. First up, a type 1 error. This is your classic false positive. It's when your study screams, Eureka, we found something, but you're wrong. The effect you're so excited about just isn't there. It's a ghost in the data. A medical test is the perfect analogy here. A type 1 error is like getting a test result that says you have a disease. You panic, you worry, but it's a mistake. You're actually completely fine. All right, then there's the flip side, a type 2 error. This is a false negative. This happens when there is a real true effect out there in the world, but your test just completely misses it. You wrap up your study saying, well, nothing going on here, when actually you were standing right on top of a major discovery. And going back to that medical test, a type 2 error is when the doctor says, good news, you're all clear. But you're not. The test missed the disease. And you can see how that could be just as dangerous or maybe even more so. And this is the crucial part. It's a trade-off, like a seesaw. You can never get rid of both types of errors at the same time. It's impossible. If you get really, really strict to avoid those false positives, to push that side of the seesaw down, you automatically raise the other side. You become much more likely to miss a real effect. It's a constant, unavoidable balancing act. Okay, so let's bring it all home. Why should any of us care about some dusty 100-year-old argument between a bunch of statisticians? Why does this feud matter right now to you? It matters because it completely pulls back the curtain on this idea of statistical significance. It shows us that this thing we treat as an objective measure of truth isn't. It's not a law of nature like gravity. It's a tool invented by people with a really messy history and a pretty shaky philosophical foundation. And knowing this history is actually incredibly empowering. It means you no longer have to just blindly accept a p-value as gospel. It gives you the power to ask smarter, more critical questions. Basically, it helps you become a much better, much more savvy reader of science. And that really leaves us with one big question to think about. If the gold standard we use to decide what's true in science is built on such shaky ground, what does that mean for how we should approach all the scientific claims we see every single day, in the news, on social media, everywhere?